The experiment in this lab involved dropping a bar magnet with a known magnetic dipole moment down a long, non-ferrous conducting tube, in this case a roll of aluminum foil. Due to Lenz's law and Faraday's law, as the magnet passes through the rings, the magnetic field at the center of each ring will change, and this causes a changing flux. That changing flux will then in turn induce an electric field in the tube, which will exert a magnetic force on the falling magnet, such that the magnetic force opposes the force of gravity, and the magnetic force on the magnet slows the descent of the magnet. This lab demonstrates the fundamental relationships described in Newton's third and second laws of motion, Faraday's law, Lenz's law, and the Biot-Savart law. The following data and observations were gathered in the lab. The dimensions of the tube are as follows. The length of the tube was 12 inches, or about 0.3 meters. The inner ring diameter from the end of the cardboard tube to the other end of the cardboard tube was 2.5 centimeters, and the outer ring diameter from end to end of the foil was 4.5 centimeters, meaning the thickness of the foil was about 1 centimeter. The magnet appeared to fall very slightly slower through the tube than in total freefall. However, the change was nearly unnoticeable and was only really detectable after watching a slow motion video. The average time it took to fall through the tube was 0.3402 seconds. Using the data from the experiment, a simulation was made using GlowScript. Here are the following major sections of the GlowScript code. The section in the top left calculates the time derivative of flux given a magnet and a ring. In the right, the force of gravity, the current of a given ring, and the force of magnetism on the magnet are calculated. These values are then used in the code included in the bottom left, which calculates the position and the velocity of the magnet. Here are the results of the GlowScript simulation. On the left, you can see a visualization of the magnet passing through the conducting tube, with the blue and red representing clockwise and counterclockwise induced current respectively. On the right is included a plot of the velocity of the bar as a function of time. As you can see, the resulting time in the tube was 0.468 seconds. Based on the code used for the simulation, the red color corresponds to the counterclockwise direction, and the blue represents clockwise. If the magnet is flipped in orientation, both the current and the magnetic field will have values opposite of the values given from the opposite orientation. Therefore, the two opposite directions will cancel and yield the same result for the net force. The time it took to fall through the tube in the simulation was 0.468 seconds, which is greater than the time it took experimentally to fall through the tube, which was 0.34 seconds. The graph shows decreasing negative velocity. The force of gravity is constant, with oppositely directed magnetic force, which is consistent with the plot shown on the previous slide. If the tube is considered to be a series of conducting rings, then cutting holes and slots in the tube will then create rings that have holes and slits in them. These rings will then be open and will not carry a current. Then, not all of the rings will contribute to the net force. Also, if the resistivity of the conducting tube is lower, then it will have a greater current. And the greater the current, the greater the force of magnetism on the magnet.